Okay, so let's get started. The first thing I thought we would do is spend just like a minute on this one question. I've returned assignment 3 here. In general, it was well done, except for question 4. Most people got question 4 incorrect. A few got it right. So it wasn't meant to be a tricky problem, but let's just go over it. Yeah, it's not tricky. So it doesn't really matter what the scenario is. There's some particle, we have a collection of particles and they decay at a rate of 20 per minute. And we want to measure the actual decay rate to within 4% of its value. How long should we count for? So the count rate will be the number of counts n divided by however long we count for t. Now, we're given some other information about the uncertainty in this count rate. So we want the uncertainty in the rate divided by the rate to be 4% or 0.04. So in a counting experiment, we talked about the uncertainty in the number of counts. What is the uncertainty in the number of counts? Plus or minus what? Sorry, I couldn't hear. One. No. So they follow Poisson distribution, and so the standard deviation in a Poisson distribution was the square root of the number of counts. So if the rate is n over t, and then we count for a certain amount of time, that's like really clearly, like we count for 20 minutes or whatever, we can make the uncertainty in the counting time negligibly small compared to the uncertainty in n. So the uncertainty in the rate is the uncertainty in the number of counts divided by t, which is square root n divided by t. Okay, so then what we could do is we could say, well, okay, sigma r over r, we know is 0.04. And now we know sigma r over r would be, well, sigma r is square root n divided by t, and the rate is n divided by t. And so the t's will end up canceling, and you end up with 1 over square root n. And so now we have two expressions for the same thing, this ratio. They have to be equal to each other. So 1 over square root n is equal to 0.04, or n is equal to 1 over 0.04 squared. And I forget what that is. It's something like 625 or something like that. This is 625 maybe. So that's the number of counts. Now that's not what we were asked to find. We were asked to find how long we have to count for. So if I know the number of counts I have to make and I know the count rate r, how do I find the time? Yep, that's right. So that's going to be t is n divided by the rate is 625 divided by 20 counts per minute. And this comes out to be, if I'm remembering correct, it's something like 31.25 minutes. So anyways, that was that last question assignment. Okay, so the keys were, we had to do a bit of propagation of error, like a simple one, and then we had to recognize that in a counting experiment, they follow the Poisson statistics, and the error in the number of counts is the square root of the number of counts. Okay, good. So, oh, that's not the one. Let's see. Okay, so let's just do a couple of announcements here. Assignment 4 is due next class, so that's Wednesday of next week. The sign up for experiment number 5, you'll have to do that by the end of Wednesday next week. So that's also March 13th. Just as a bit of information, I've posted assignment 5. So it's on the course website. So if you haven't started assignment 4, just make sure the one that you do for next week is assignment 4, not assignment 5. If you want to work ahead, after today's class, you'll have everything you need for assignment number 5. And then I just wanted to remind you that formal reports has a due date that's not going to change. And that is April 10th. It's the second last day of classes. It's also a Wednesday. So I recommend that you start working on your formal reports. I know that some of you have, so that's good. Okay. So what we were talking about last time is we imagined we measure some data, xi as a, so we set x and we measure the response the response y plus its uncertainty. So we have this xi and yi plus or minus sigma I data set, and we imagine we have n sets of those values. And we're assuming they follow like a linear trend. So if we plot them, they follow kind of a straight line, and we want to fit it to this expression and determine the best value for the intercept and the slope. And in fact, we did all of that. We worked it out. We said, okay, the best possible value for the intercept is given by this expression, and here's the expression for the slope. We did this by doing a maximizing the likelihood. So we found the probability that we would measure a particular data set, and we did a maximization with respect to A and B. That led to a system of 2 equations and 2 unknowns. We ended up writing them as a matrix equation and then doing a bit of matrix algebra to find the solution. So today, what we want to do is we want to apply propagation of errors to these equations for A and B in order to find our confidence in those best fit parameters. How certain are we about their values? One thing to notice, both these expressions for A and B involve this delta. Delta was the determinant of that matrix we wrote down, and it has this kind of form. The one thing I just want to remind you of is that delta does not have any y coordinates in it. It has just x coordinates and the uncertainties. That's important because when we do propagation of errors, what we're going to have to do is we're going to have to take a bunch of partial derivatives with respect to the y coordinates. And so because delta doesn't have y in it, we'll be able to treat it like a constant. The other thing I wanted to remind you of is our friend, the Kronecker delta. So we're going to take derivatives that look something like this. The derivative of yi with respect to yj. And so I, for example, could be 7 and j could be any integer. If j is different than I, then this derivative is going to be 0. If I and j are equal, the derivative is going to result in a 1. And we represented that as the Kronecker delta. And the Kronecker delta was our good friend because if it exists inside a sum like this, so we have some function of some variable that has an index I, and we're summing over I, and that function is multiplied by this delta function. What you could imagine is, let's just take j equals 3 for this example. Then we do the I equals 1 case. We're going to get delta 1, 3, 0. Delta I equals 2, 2, 3, 0. Delta 3, 3, that's going to be a 1. So the only term that will survive this sum is the one where I equals j. And so this whole sum gets collapsed into a single term, and that term is just f, and the index gets changed to x sub j. And so we're going to make use of that today. All right, so let's give it a shot. So the question is, what are the uncertainties in A and B? Okay, so A is going to be a function of all of the y measurements. And B is going to be a function of all of the Y measurements as well. Okay, so what we're going to have to do is we're going to have to say sigma A squared is going to be the sum of j equals 1 to n of the derivative of A with respect to yj times sigma j squared. So that's the propagation of errors. And so there's the partial derivative that we're going to have to evaluate. We're going to have to do the same thing for B. Well, for every single term in B, or for every value of y1, 2, 3, up to n, we'll have to do d by db, db by dyj times sigma j squared. Now you might be looking at this and say, well, there's a bunch of x's in our expressions for A and B. Why don't I have partial derivatives with respect to x? The reason is that we're assuming that the uncertainty in the x values is negligible. So we could have derivatives with respect to x, but then they would be multiplied by like the sigma x values, but we're assuming those are all 0 or negligible. So that's why we consider only the y derivatives. Okay, so let's first note that delta is independent of yj. Okay, so we're going to start by evaluating. We'll do the partial derivative of A with respect to yj. Okay, so we'll evaluate the derivative. Then once we have the result, we'll come and we'll put it back into the sum. And then that will lead to the uncertainty in our intercept. Okay, so let's see. A had, first of all, there's a 1 over delta, which we said is independent of y. So that's a constant. I'm going to pull it outside the derivative. Then I have the derivative with respect to yj. And then it has to act on a bunch of stuff. In fact, I kind of do this all the time. I'm going to give myself some more space here. So let's just quickly scroll back up here. Our A expression, we've already written down the 1 over delta. It's x squared over sigma squared, y over sigma squared, minus x over sigma squared xy. So it's x squared y x xy. Okay, let's see if we can do that. So we're going to have, whoops, xi squared over sigma I squared. Then we had y. Then we had a minus x. And then we had xy. Okay. So this is what we're going to have to work on. The derivatives can move in and out of these sums. These are sums over I, and this is the derivative with respect to j. This term has no y in it, so it's a constant. So this derivative is going to act only on the second sum, and I'm going to take it inside the sum. So we end up with a 1 over delta sum of xi squared sigma I squared. Then we have the sum of 1 over sigma I squared, and then I have dyi dyj. Okay, and then we have minus. Again, this first sum doesn't involve y's, and so nothing happens with that one. And then we have a second sum. There's a xi over sigma I squared, and then we have a derivative of yi with respect to yj. Okay, so I think that's what we've got. These derivatives we know give the delta function. So once you're comfortable with this, you would just go directly from here to killing these sums, but I'll write this out in a few steps so that hopefully that will make it clear what we're doing. So we have our 1 over delta, and that first sum, nothing changes. And then we have, whoops. The second sum is going to be 1 over sigma I squared. And then we have a delta ij. What is, what's the sum going to become? So I is going to have to be equal to j, that's true. Like what, if I was to write down the total result of all of this, what is it going to be? One over sigma j squared, that's right. So, you know, we could just, let's just do a bit of an aside here. We could just write out the terms of the sum. So the sum of 1 over sigma I squared delta ij is going to be equal to 1 over sigma 1 squared delta 1j plus 1 over sigma 2 squared delta 2j. And it would go on. There'd be a special one where I is equal to j, delta jj. And then there'd be some more terms, and then we get to the last one, 1 over sigma n squared delta nj. But when we do this, every time j is not equal to I, the delta is going to be 0. 0, 0, 0. And every time it is equal, which happens only once, that delta function is going to be a 1. And so ultimately, all you get is 1 over sigma j squared. Okay, so that's right. So that's our little aside here. Then we have to do these next ones. The xi over sigma I squared. Nothing happens there. And then we're going to have this other sum. It's xi over sigma I squared delta ij. What's this one going to evaluate to? Xj over sigma j squared. That's exactly right. Okay, perfect. So then let's see. All right. So then what we end up with is this a derivative, or the derivative of a, dA dyj is going to be equal to, there's a 1 over delta. And then let's see, we're going to have the 1 over sigma j squared. I'll write that first. And then we have the sum of, what was it? It's xi squared over sigma I squared. That's right. Yeah. And then minus, and then we'll have xj over sigma j squared. Okay. And then we have the sum of xi over sigma j squared. Sorry, sigma I squared. Right. Okay, so everything inside the sum right now has an I subscript, and then everything not in a sum has a j subscript, and those j subscripts came from that delta function. Okay, good. So what we're going to try to do is, if we call this equation 1, let's say, we're going to sub this derivative back into equation 1. So let's sub dA dyj results back into equation 1. Okay, so I'll write down equation 1 again, just so we have it. in front of us. So it was j equals 1 to n of the derivative that we just evaluated times sigma j, and then square the whole thing. Okay, it'll get more messy before it gets better, but that's okay. That's just how life is in general. Messy piece of shit. Okay, so let's go. We're gonna square this derivative. There's a 1 over delta out front, and so there's a 1 over delta squared. Okay, then we're gonna have the sum of j equals 1 to n. Now, we're gonna take our derivative and multiply it by sigma j. Both terms have a 1 over sigma j squared in front of them, and so we'll get a cancellation with this sigma j. So first of all, we get 1 over sigma j. We cancel one factor in the denominator, and then we should have the sum of xi squared over sigma I squared. That's right. Then we have a minus sign. Then we have an xj. Then we cancel one factor of sigma j. And then we're left with the sum of xi over sigma I squared. And then we have to square everything. Okay. Right. And so it's this extra square that makes things messy. But let's just write it out. There's nothing to do but expand the square. So 1 over delta squared, the sum of j equals 1 to n, and we're just going to get a bunch of terms. So we square the first one, so we're going to get 1 over sigma j squared, and then we have this sum of xi squared over sigma j squared. Sorry, sigma I. I got to keep my subscripts correct. That's squared, and then we square the whole thing. So that's just the first term. Let's do the next term here. We'll square this one, and then we'll do the cross term. So when we square it, the minus sign goes away. So we get a plus. And then it's xj squared, sigma j squared. And then we have to square this whole sum, xi sigma I squared all squared. Okay, good. And now we have the cross term. We'll get 2 copies of the cross term. There'll be a minus sign. We'll get xj, sigma j, and a sigma j. So the sigma j gets squared. So we should get a xj over sigma j squared. And then we just have the product of the sums. So it's, which one do I want to write first? I guess I'll write the xi squared sigma I squared, and then we have a sum of xi over sigma I squared. Okay, I think that's everything. Okay, so believe it or not, this is going to end up simplifying a little bit. What I'm going to do is I'm going to distribute this j sum. So it's only going to act on stuff that has a j subscript. So this sum acts only on this part, and then it gets all multiplied by this. Then it's going to, that sum will act on this part, and then on this part. So we will distribute the sum. All right, and what we're calculating is sigma a squared. All right. So we'll keep the 1 over delta squared here, and then we'll have the sum of 1 over sigma j squared times this xi squared over sigma I squared all squared, plus the sum of xj squared sigma j squared, and then we have the xi over sigma I squared sum all squared. And then we have minus 2 times the sum xj sigma j squared. And then we have let's see, I'm gonna clean this J up a little bit. Sigma J squared. And for this next one, I'm gonna change the order of this. I'm gonna write this sum here, and then I'll write this one over there. It doesn't matter, but I'm just gonna change the order. And we'll see why in a second, I hope. And then we have the xi squared over sigma j squared sum. All right. What do you know? What do you notice about these two sums? They're the same, yeah. They have different indices, but these are both sums from, like this one is from I equals 1 to n, and this one is from j equals 1 to n. I don't care that the indices are different. We're summing the same values over the same range. And so this is just the sum of xi over sigma I squared all squared. Okay, well then, if you look at this is xj squared over sigma j squared times the sum of xj over sigma xi over sigma I squared squared. So this sum is the same as this one, and this squared thing is the same as this squared thing, and so we're going to end up getting the cancellation between these two. So we'll write it out in detail. So this is 1 over delta squared. And so, okay, nothing happens at all to this first set of sums. Okay, then I won't change anything with the second set of sums either. Okay, and then we have -2. And then let's see, I'll write the xi squared over sigma I squared sum first, and then we'll have the sum of xi over sigma I squared all squared. Good. And so this and this are the same except for the -2 out in front. And so we can cancel this if we cancel the 2. So finally then, sigma A, well, it's not finally, because it's gonna get even better. It's exciting, I know. So 1 over sigma j squared, and this is xi squared over sigma I squared squared. Then we have minus xi squared over sigma I squared, and then this is xi over sigma I squared squared. You're right, it's squared. Yes, thank you. Okay, good. So one thing we're going to do now is we're going to look at the two terms and try to identify any common factors. Are there any factors in this term and this term that are common? So there's a 1 over sigma squared sum here that doesn't exist here. So that's not common. There's yeah, this xi squared over sigma I squared is in this term, and it's in this term. We have 2 factors of it here and 1 factor here. So we can pull out 1 common factor. And so the common factor is this thing and then 1 of these powers. And so if we factor that out, we would, so let's factor out this common sum. Okay, so we would get sigma A squared is equal to 1 over delta squared, and we factor out an xi squared over sigma I squared sum. And then we have in our square brackets 1 over sigma I or j, doesn't matter, squared, And then now we get just one factor of xi squared over sigma I squared minus, this has been removed, and so we just have this thing here, xi over sigma I squared, all squared. Okay, this is where the magic is going to happen. Does anyone recognize this thing in the square brackets? Let's go back to the beginning. What is it? Sorry, I think I heard it. It's delta. Yeah, that's exactly what it is. 1 over sigma. They all have 1 over sigma squared, right? So let's just accept that. So we have a 1x and then x squared. Sorry, 1x and then x squared. Okay, and then we go back to what we have here. So it's 1 x squared. Oh, sorry, did I what was delta? Did I have just an x there? Yeah, I think I probably have a typo here, because I think that should be yeah, this is a typo. That should be a squared. Okay, so you're right, it is delta. I just wrote it down wrong here. I'll check the notes from last time, but that should be a squared. So all of this ends up being delta, which of course is going to cancel with one of the 1 over delta squareds, and you end up with, therefore, sigma A squared is equal to 1 over delta, the sum of xi squared over sigma I squared. And let's just make sure that that's right. Yes. Oh, that's fun. Why did you do that? Share screen. Okay, good. So this is the uncertainty and the best fit value for the y-intercept. You could do basically the exact same calculation for the uncertainty in the slope. I'm not going to do it. It's very similar, except you start with a slightly different version of the parameter A has parameter B has slightly different sums than parameter A does. So if we go back to here, B. So it's similar in that always the first sum is not going to involve y, so the derivative is only going to act on the second sum in each term. The only difference is you're going to end up with an x coming out of this one when you take the derivative over here instead of over here. Otherwise, all the calculations exactly the same. You still end up getting the delta, which is going to do the same kind of cancellation that we did at the end. And so I'm just going to write down the results for the uncertainty in the slope. So using the same methods, you can find the uncertainty in the slope. Is given by Okay, so what you would do is you would say the uncertainty in the slope squared would be calculated using propagation of errors. So you take the derivative of b with respect to yj, multiply by sigma j, square it, and then do the sum over all n measurements. And if you do that, what you're going to find is the uncertainty in the slope squared is equal to 1 over delta. Turns out to actually be even slightly simpler. It's just 1 over sigma I squared sum. So this is the uncertainty and the best fit value of the slope. What's nice about this is, usually people think of uncertainty calculations as being like difficult, right? And so fair enough. They tend to be long compared to other types of calculations, compared to other calculations. But if you look back to how we would have to calculate the actual value for the intercept and slope, we need to know delta already, and we need to know the results of these two sums because they appear in our calculations of A and B. So when we find A and B, we've already evaluated all these quantities, and so there's no extra work to find the uncertainties because we already know these results. We just have to multiply the right values together, and the sum drops out immediately. Yeah.
That sigma, is that just the error in the y values?
That's the error in the y values. Yes, that's exactly what it is. So yeah, we've made measurements of x and y plus or minus sigma. And so the sigma values are the uncertainties in the y. Yes. Okay, now, how are we doing time-wise? We have about 13 minutes left. Okay. So Michael asked a question at the end of last class, and it was a good one. It was something like, when I do linear fits in Python, Python talks about this covariance matrix, and it finds the uncertainties and the best fit parameters from this so-called covariance matrix. And so what's that all about, and how does it relate to this? I think is the essence of the question.
Yeah, pretty much.
Yeah.
There's like a command line.
Yeah, even if that's not the question you're asked, that's the question I'm going to answer. Okay, so recall from last time. So from last time, we said something like, we're trying to find the values of A and B. So we had, let's see, let's just actually look at what we had from last time. Let's see if we can find it. Is this us? No, that's 120. Is this us? Yes. And so we had this big mess of a thing. We had this covariance matrix. And so what I'm going to do is I'm going to copy a bunch of stuff here. So let's copy. Yeah. So I'm going to copy this stuff. Copy. And then let's go back to today's notes. Oh, right. That was our example problem. Is this today's notes? Yes, from last time. Oh, paste. Okay, so we had the following. So this is our system of two equations that we got when we tried to maximize the likelihood probability. And then we identified everything in terms of these U's and V's and these UA's, UB, VB, VA stuff. And we wrote that down as a matrix. And of course, what we were trying to find was the values of A and B. So what we could do is we can define this thing to be matrix A. And so I'll use A with 2 lines underneath it to represent a matrix. So what we ended up with is UV was equal to the matrix times this AB. In order to find AB, we multiplied both sides by the inverse of A. And so we ended up with AB was equal to the inverse of A times UV. And the inverse of A was 1 over the determinant of A. And then who remembers what's the inverse of a 2 by 2 matrix?
BB and minus BB minus B and
So let's see, I think I might have it written down here.
B minus
Yeah,
B.
yeah, the VB is positive, and then it's a minus UB. Yeah, minus VA, and then the other one is a UA, right? Good. Yes, that's what it was. This determinant of A, that was what we call delta. And so this was just 1 over delta VB minus UB minus VA times UA. Okay. All right. So, and then, okay, I guess I've dropped my UVs here. So what we have is then our AB was equal to this stuff. Okay. So it turns out that this A inverse, which involves this 1 over the determinant and this square matrix, this is exactly what people call the covariance matrix. So this is called the covariance matrix. So for linear fits, the covariance matrix is given by, okay, 1 over delta. And then what I want to do is I want to write out, instead of like these VBs and UAs and all that stuff, I want to write out the full covariance matrix in terms of the actual sums. So we need the VB. VB is x squared over sigma squared. So it's sum of x squared over sigma squared. And then UB is x over sigma squared. Okay. And it's a minus sign. Sigma squared. This is I. And then we need a VA and a UA. Let's see if we can remember both of them. VA is x over sigma squared, and UA is just 1 over sigma squared. Okay. So it's minus x over sigma squared, and then UA is just 1 over sigma squared. Okay, good. Now, what I want to look at are the diagonal elements. The 1, 1 diagonal position is x squared over sigma I squared times 1 over delta. And that's exactly what we calculated for sigma A squared. If we look at the other diagonal element, it's just 1 over sigma squared times a 1 over delta. This is exactly what we didn't calculate it, but we wrote down the result for the error in the slope. So what I want to recognize is that the diagonal elements of the covariance matrix give us the square of the uncertainty in the best fit parameters. I mean, it's kind of an amazing thing if you think about it, because if we want to solve our minimization problem that we did last class, using the matrix algebra, we have to take the inverse of that A matrix, which is the covariance matrix, and just the fact that we've taken that inverse, we already instantly get the uncertainties. So that's a nice little treat. So here are the two diagonal elements, and so the 1, 1 element gives sigma a squared. So we have sigma a squared is 1 over delta sum of xi squared over sigma I squared. So you just evaluate that sum, then take the square root of the total result. That's the uncertainty and the intercept. And the 2, 2 element gives sigma b squared. So sigma b squared is going to be 1 over delta times the sum over 1 over sigma I squared. Okay, good. And I think that's where I'm going to stop writing stuff down. The assignment 5, which is not due for a while, it's like, I'm pretty sure it's March 22nd, which is a Friday. So it's not Friday next week, it's Friday the week after. But in that assignment, what you're going to do is you're going to do a couple of linear fits. And for one of them, what you're going to have to do is you're going to actually manually calculate the best fit parameters A and B. And so you're going to be given some data, some X and some Y plus or minus sigma values. All you have to do is evaluate all these various sums, figure out what this delta is, and then plug them in to get the A and B. And then what you can do is take the data that you're supplied with, calculate these sums, take the square roots, and you'll have the uncertainties in your parameters. Then you're going to take that same set of data, you'll do a linear fit in, say, Python, and you want to compare the results that you get to the results that Python spits out, and hopefully they're close. Okay, so that's the idea with assignment number 5. It's not a difficult assignment, but I think it's useful to know what these fitting algorithms are doing. And in the case of a linear fit, it's pretty simple. There's no guesswork. You're just calculating exactly what the best values and the uncertainties of your fit parameters are based on the set of data that you've measured. Okay, good. So thanks very much. Have a good weekend. And we'll see you. Well, we'll see some of you on Tuesday, the others on Wednesday next week.
We were